So in the previous video, I showed you how you convert this circuit into a simpler circuit, closed loop connected, so that you can easily use nodal analysis or mesh analysis or superposition in order to find the voltage VI and VO. So in this video, hopefully I'm going to show you how you actually calculate the VI and VO. Okay, so using superposition, we can turn off a voltage source, turn off all voltage sources except for one, and find that effect on the resistor or other capacitor or other components, and then turn that one off and turn another one on, and in that case we can find the individual effects by the voltage source, add them up, and that will give us our total effect, which is what the superposition principle states. So first I would like to turn off the voltage source, and as you can see over here, I short-circuited because voltage sources are short-circuited when you turn them off, whereas current sources are open-circuited. So if I short-circuit this, then I'm going to be left with the two voltage source, 5 volts here and 5 volts here, and I can turn this one off, short-circuit this one as well, and find the effect of this, then short-circuit this and find the effect of this. But there's no point, because these two voltage sources can be combined to a single 10-volt voltage source. And also what's very important is that notice that a capacitor is short-circuit to DC. A capacitor is short-circuit to DC, and open circuit to high frequency AC. Whereas if you can remember, an inductor would be the opposite. But in this case, capacitor, so this is open circuit, which means even though I short-circuited this part is an open circuit. Which means if I redraw the circuit, it's going to be something like this. Something like this. This is a plus 5 volts going out here. It's hitting a minus 5 volts and is bumping up again 5 volts. So in other words, I'm pumping up 10 volts in total. Because if I assume this is ground, then this is 5 volts coming out and then bumping up again 5 more volts, which I can simply write as 10 volts pumping up. This is the node, which will give us our VO plus, which is connected to ground. But we also have to note that because this voltage here was 0 volts when we set this as ground, then when I connect it to this in this form, then I have to remember that then VO will be respect to 5 volts, which is the average between the two. Because in this case, this VO was the average of these two, and you can see that this part of the circuit is an average of the 5 volts and minus 5 volts. But that will come later. So the point here is just to find the voltage drop between the individual resistors. So in the previous circuit, this was a 3.9K, and this was a 10K. And if we do mesh analysis, this is just simple circuit, we can just find I0. Just find the current I. We're going to call this I1 because it's superposition. Then we can see that the equivalent resistance is 13.9K. The voltage is 10 volts. Ohm's law gives us I is equal to V over R, which is equal to 10 volts over equivalence is, as we said, 13.9K, which gives us the currents. Which gives us a little space over here, 1 over, my bad, let me just calculate it quickly, 10 divided by 13.9, which gives us 0.719, so 0.719 milliamps because we divided by K. So in other words, I1 is equal to 0.719 milliamps. Well, then if we find the I1, then we can simply find the voltage drop caused by these two voltage sources, which we're gonna save for later. Then what we can do is using superposition now, turn this Vs on and find the input voltage. Okay, so if we turn these two off, then basically what we're doing is we're short-circuiting it. So we're gonna have something that looks like this, okay? We have an AC Vs. I guess I'll pause the video and then resume later. So I drew the circuit over here. Notice that the question states that we can assume that the capacitor will be a short circuit, given for the AC current, because the AC is meant to be 20 kHz. So if we have this, then we can simply find I2 by finding the R equivalent. So R equivalent will be equal to, well, the parallel of this, so 1 over 10 plus 1 over 3.9, and this, I'm going to assume everything in K from now on, then plus this, which is 2.2, and then plus 0.6. And this value will give us the R equivalent, so I'm going to quickly calculate it, which gives us 5.6K, assuming these are K values. Now that we have R equivalent, well, then we can find the current going through here, which is using Ohm's law. V is equal to IR, so I2 is equal to Vs over 5.6K. And now Vs is actually given in the question to be 2 volts amplitude, 20 kilohertz. And then we can convert Vs to the root mean square, and then use it just as a DC would be used. So the amplitude is 2 volts, which means Vs, the RMS, the source voltage in root mean square, is equal to 2 volts divided by root 2, which is equal to root 2 volts. So now we have that the RMS, we can plug it in here. So that's going to equal to root 2 volts over 5.6K, which is equal to, I plug in the calculator, root 2 divided by 5.6, which gives us 0.25 milliamps. So this current here is equivalent to 0.25 milliamps. Although it's AC, we're going to use a root mean square, simplifies it, 0.2 milliamps coming here. And I'm going to stop from here. I'm going to stop it here. But then, given the current coming here, you can use the current division to find the current going through individual ones. Then you will find the voltage drop across these two. And we can combine that with the fact that we already know this I current coming. So we're going to find the voltage drop caused by this current plus the voltage drop caused by this current. And the most important part here is keeping the signs. So if this is going to be, if you're going to call this a plus and a minus over here, then you got to be assuming that this is a minus and this is a plus. Because this node over here is the V out node. So the 3.9 is negative with the V out, which means the 3.9 must be also negative with the V out, and same with the 10 as it goes on. So given that, you're going to find the voltage drop caused by this current. Let's say it's going to be, I don't know, 0.2 volts. And then you're going to find the voltage drop caused by this current, which would be, let's say, 0.4 volts, which means the total voltage drop across that resistor is 0.6 volts. And given that, then, you can, let me go back to the circuit, you can then know that if the voltage drop across these two is, let's say, something, let's say 3 volts, and this is a minus 5 volts, then this node here must be at minus 2 volts. If this is a 3 volts difference from here to here, and this is minus 5, then this must have been minus 2, because that drop in 3 volts that caused the resistor sent it to negative 5. So then if this is minus 3 volts, then with respect to ground, we're going to say V out is going to be, if this is minus 2 volts, then V out would be minus 2 volts. And that should be it. You're going to find V out, and the voltage of V out, the voltage of V in, and then you can see what the amplitude, what the amplification or the graph of it would have looked like. So hope that helps.